Hello everyone, welcome to another video. Today we're going to be introducing differential equations. In order to do this, we're going to have to go through some definitions, particularly in regards to how differential equations are classified. And here we will talk about the three types of classifications of differential equations that there are. They include type, order, and linearity. And that's what we're going to talk about today. And then we'll also talk a little bit about the solution to a differential equation and what it means. So this video is primarily going to be concerned with the foundational definitions that make up the structure of our differential equations study. So let's start. The classification of DEs. Let's define what a differential equation is. It is simply an equation containing the derivatives of one or more of the independent variables. Okay, so it's an equation that contains a function and its derivatives. Now, these classifications, the first classification that we will discuss is the type of differential equation. We have ordinary differential equations, and these only contain ordinary derivatives. So you'll see the operator d over dx a lot, of some function y, maybe the second derivative plus, the first derivative, and then maybe some coefficient here or whatever. So these will just contain ordinary derivatives, not partial derivatives, which contain this symbol, right? These are different. These are partial derivatives. So these ordinary differential equations, they can be the derivatives with respect to a single independent variable and one or more dependent variables, okay? So here are some examples here. The first one, this dy dx plus 4y equals sine x. This right here, it's an equation containing a function y and its derivative with respect to x. So you can see we have y here, and then we have the derivative of y here, and it's with respect to x. And then we have this thing over here that we'll talk about later. It's called a forcing function. We're not going to talk about that yet, but that will be used in future methods of solving differential equations. So this second one here, this shows that we can have higher order derivatives. These are still ordinary derivatives. They're just higher order derivatives of that same function with respect to a single independent variable, right? Just like it says right here. And so with this, we have two equations, but this third one here, this one says that the number of dependent variables can be greater than one. So you can have the dependent variables in this case are x and y, which are going to be functions of t. We can just see that from the derivative operators in this equation. And then again, on the right, we have this forcing function here. Okay, so those are the ordinary differential equations, abbreviated ODE. Now the second type in our classification scheme is the partial differential equations, the PDEs. And this is very simple. It just contains partial derivatives of one or more dependent variables of two or more independent variables. So notice that we can have more independent variables. We can have one more independent variable than we do dependent variables. And there can be one or more dependent variables. As you can see right here, we'll go through these examples. Partial derivatives with respect to two independent variables. These are independent variables on the bottom, if you remember that from calculus. And there's one dependent variable, which is u. That's the function that we're trying to solve for, and we'll get to the solutions of these DEs in a second. Similarly, they can be of higher order as well. And also, we can have like identities, right? So we can say like, oh, the partial derivative of u with respect to y is just equal to the negative of the partial derivative of x with respect to t. And you can see here that we have two independent variables and two dependent variables. The next type of classification that we can go through is the order. This is pretty simple to identify. It's just the highest order derivative that appears in the differential equation. That will be the order of the diff EQ that you are analyzing. And they can contain either ODEs or PDEs, ordinary differential equations or partial differential equations, ordinary derivatives or partial derivatives. Now, here is an example. You might be tempted at first if I asked you, what is the order of this differential equation right here? What is the order of this? You might be tempted to say it's 3, right? Because you have like this right here. But the thing is, this is an exponent. This is not to be confused with the order of the derivative. And so it's the highest order of derivative. So in this case, it would actually be 2 because 3 does not count as an order of the derivative. It is simply just the power that is raised, which actually makes this nonlinear, and we'll talk about that in a second. So we're going to talk about some different forms before we move on that a differential equation can take, right? So this function m of xy times dx plus n of xy times dy, so these are functions in two variables, equals 0. So now we assume, because it's not clear from the notation here what the independent or dependent variable is, but if we just assume that y is the dependent variable, we can actually just divide through by dx, and this will give us this structure right here, which is an alternate form. And then we can also just solve for the derivative of y with respect to x as this negative ratio between m and n, the two functions in two independent variables. Now, to express an nth order differential equation that has only one independent variable, you might see it like this. This is more of a theoretical construct, and we won't really use this a whole lot, but it is good to understand. So the differential equation can be written as if it were like a function, and then the arguments inside were the independent variable, and then the dependent variable and its derivatives, right? And the highest derivative in this differential equation is n. We go from the 0 derivative, 1 derivative, 2 derivative, ... n minus 1 derivative, n derivative. Now, this equation can be expressed in terms of this highest derivative of y of n. So by just moving it to the other side, we have this expression here. So the nth derivative, the highest derivative, can be solved for by the remaining n minus 1 variables. And I believe I wrote that here. This is called the normal form. This right here is the normal form of this above equation here. So the small f is basically used to define the highest derivative in terms of the independent variable and the remaining n minus 1 derivatives. Now, just an example to show and build an intuition for n. So the first derivative, that just indicates that n equals 1. And it's going to be equal to this little f of xy. So some function in terms of x and y. Similarly, the second derivative, n is going to equal 2 for that one, right? We're just replacing n with 2 in this derivative operator. But notice also now we have 3 input arguments here. We have the independent variable, we have the 0th derivative of y, which is just the function itself. No derivative is mathematically the same as the 0th derivative, and then n equals 1 right here. And then remember I said the highest order term, the highest order derivative, can be defined by this normal form using the remaining n minus 1. In this case, n is 2, n minus 1 is this right here. So we have n minus 1 variables here, n minus 1 derivatives. Now, similarly, if y, this is just n equals 0, right? That's just the 0th derivative. So again, that's just what I was saying. No derivative is technically the same as a 0th derivative, i.e. this. However, we would never write that. You could just write dy dx. All right, so the third type of classification that we use in our analysis of differential equations is determining the linearity. Is it linear or is it nonlinear? In order to understand this, we have to understand what the form is of a general nth order linear differential equation. So we basically have to have y. The differential equation has to be linear in y. There can't be any sine of y or sine of the dependent variable or the dependent variable cubed or a derivative squared or cubed, like we saw in the earlier example where that dy dx had a cube on it, and we thought we might get confused with the order of the differential equation versus the powers associated with them. And those powers in that case, where dy dx was cubed, that makes it non-linear, because this differential equation, because of this, is not linear in y, in the dependent variable. Okay, so that is what linearity means, and you'll typically see it in this form. So you'll have 4 terms on the left-hand side of the equation, and then you have some forcing function g of x on the right-hand side of the equation. The special case for n equals 1 and n equals 2 they just look like this. So these, we have methods to solve them pretty simply, and we're going to go through a lot of different methods to solve these types of equations. But you can see right here, you have some function of x. It can be a constant too. This doesn't have to have, it doesn't have to be necessarily a function of x, but a1 of x could equal 6 or something. But it can also equal 6x or 6x squared, e to the x. There's all different types of nonlinear coefficients that we can have for this a of x function. Or coefficient, I should say. This is the coefficient. These are the derivatives. Sorry, coefficients. And then these are your the derivative of the dependent variable and the function of the dependent variable. And then this forcing function here. Similarly with n equals 2, this is just a second order linear diff-eq. Again, you can see this because there's no nonlinearity in y. Y is and also the derivative is a linear operator. So just by taking the derivative of y, that doesn't take it out of its linearity. And so we can actually just add these two together to test for linearity and see if anything changes, right? Let's see if like the structure of it changes. And so by adding these, I get this expression here in green. And then I'm going to say that let's say b equals 2a, right? And then we can substitute those b's in for 2a and let this transformation happen, right? G of x goes to h of x. And after this addition, y and its derivatives, they remain in the first order. So, and you can see where I defined these parameters here, but it didn't change the linearity of y. So the equation is linear. When you add them together, it checks out, everything works. So what we should take away from all this right now is that the coefficients, a and b up here, they can depend at most on the independent variable x. That is the whole idea. And then a nonlinear equation, which is simply just an equation that is nonlinear in any of the terms for the dependent variable. So just the opposite of what I was talking about. Nonlinear terms that you'll see, if assuming that y is the dependent variable, which it is in this case, in this whole lesson, assuming y is the dependent variable, you've got these nonlinear functions that involve y. Not good. Y to the n when n is not equal to 1. Sine of y, that's trig, that's not linear. And e to the y is also not linear. Similarly with the logarithm and all variations of that, natural log and everything, those are all nonlinear terms. So basically what I did was I determined that any additive operation between any such equation will result in a nonlinear equation. And that's why our test, if we had these right here and we plugged it in up into this addition test, this linearity test, we would not end up with a linear situation in y. And then if I just show this an example, we've got, and I did two nonlinear equations, but even if only one of these was nonlinear and the other one was linear, this would still come out to be nonlinear. So it contains nonlinear terms in y, nonlinear equation. All right. I think enough has been said on that. Let's talk about the solutions to differential equations. So in algebra, typically you would solve for a variable and it would have a real number value or maybe sometimes a complex value, but nonetheless you would get some value. Differential equations are like a step up from that. So now we're going to take it up to the next level. Our solutions to our differential equations are going to be functions. And we're going to call that function that, and it has to be defined over an interval. So we have to take into account the interval. And the function has to possess at least n derivatives on that interval I. Okay, so we have to be able to take the derivatives as many times as the highest order of the diffeq in the interval that we are considering. And then, so when you substitute this function phi into, I can't remember if that's phi or psi, but when you substitute that into the differential equation, the solution, phi, if you plug that into the diffeq, it will reveal a true identity. So key takeaway from this video is that the solution to a differential equation is a function. Phi of the independent variables, and so it's different from algebra, right? Because the solution to an algebraic equation was a number. that would solve the equation, and then when plugged in would result in a true statement. This is the same idea, but now we're going to plug in a function, and it's going to result in the same type of identity. And then up here, I just did a quick example to build some intuition. So we need to verify that this function, phi of x, so we're going to be given that solution to a differential equation. So we're given the differential equation right here. This is our function. So I'm going to label these. So this is the diff EQ. This is the function. And then this is the interval. All real numbers. Okay. So that's typically what you'll be given when it says to just verify. Later on, we're actually going to find what phi is. But for now, we're just going to figure out what's going on. So how do we go about this? Well, we're given y, the zeroth derivative of y, right? Just the function. And then in our diff EQ, the derivative of y appears, the first derivative. And we already have y here. And so what this means then is that we need to take the first derivative of y if we want to start plugging into this equation, right? And so let's just do that. Taking the first derivative of y, we have d over dx of the quantity 1 divided by the quantity 1 plus x squared, end parentheses. And if I rewrite this using exponents, negative exponents, I can bring the 1 plus x squared up to the top, from which I can then just use the chain rule to evaluate, right? So I decrease the order of this exponent up here according to the power rule, and I bring it down to the front. That negative 1 just turns into a negative sign here. I've reduced the power, and then I have to take the derivative of this inside function also and multiply that to what I have here, which is, so derivative of 1 is 0, derivative of x squared is 2x, and that's how I get this. And simplifying, this is my derivative. So now what I can do is I have dy dx. This is what dy dx is. We just took the derivative of y. And then once I have that, I can just plug it into my equation here, which I have done. And it turns out that really, if you kind of just see right here that if I just move this up into the denominator, we have the same quantities here and here, and one's negative and one's positive. Well, negative a plus a, right, equals 0. That's true. According to our, excuse me, according to our differential equation right here, this has to equal 0. And in fact, after we take the derivative and plug it in, the differential equation is satisfied. It results in this identity, 0 equals 0. You might get like 1 equals 1 or whatever. As long as the identity that you get is true, then you have solved the differential equation. So the solution, we verified then that the solution y, or we can actually just call this that. They use phi for like a general thing, but it solves the diff EQ, which is given right here. And so we can also do something extra. This is kind of extracurricular. But we can determine like the endpoint behavior. So we know that the interval is from negative infinity to positive infinity. We can determine the kind of behavior that it exhibits. So like as x goes to positive infinity here, this differential equation converges to 0. And I did that just by taking limits. So essentially, I take a limit of our derivative, and the derivative goes to 0. And then I also take the limit, I take the limit of the derivative as x goes to positive infinity, and then I also took the derivative as x goes to negative infinity to find the behavior on the left-hand side. and that derivative also converges to 0. And so this is pretty fundamental. So this is the first lesson on DiffEQ. This is an introduction, and I'm going to wrap it up here. If you like the video, just press the button and let me know in the comments if there's anything else you would like me to clear up or anything that you need me to cover in the future, and I would be happy to oblige. And thank you for watching. I'll see you guys in the next one.